You do speedruns?
So, yeah, I do. Um,
Which
so I can
game?
actually show you real quick because we're waiting on the others anyway. Um, Interesting how it logged me out. But if you look at, so one of the things I do is just category extensions for Minecraft. If you look at Chunk, so SSG, Vep, that's one of the people in my speedrun server. RS, that's me. Setseed, that's someone in my speedrun server. And
But you
especially,
have speedrun for Minecraft? What?
yeah.
What? You can
Um,
finish Minecraft? I didn't even know.
well, Minecraft has the Ender Dragon at the end. But this category, Minor Chunk, is the goal is to just create one chunk of air. Um, so one 16 by 16 area, just mine it out, which is incredibly parallel. So actually, this relates pretty well to parallel computing. We were like, okay, we've got in our university Discord, we were like, okay, let's do a speedrun together, and it was horrible, but we got world record because we were the only idiots dumb enough to put 10 people in one speedrun.
Yeah.
And there was a 10 plus category, and we were the only ones with a place in it. So we were like, what can we do that to? But then that not everyone is fucking bored out of their asses. And we're like, well, mine a chunk, like mining, that's very parallelizable, right?
Yeah.
So that's like, we got the entire chunk down in 4 minutes. Yeah, 4 minutes, 30 seconds to clear an entire chunk of fucking, uh,
Wait, which
entire chunk of
You did
like
the first
blocks.
try or how many tries?
Well, so the biggest part of it, honestly, is the seed finding. So I have written seed finding algorithms and seed finding libraries that people use to find the seed that gives us a world like this. Because this is a set seed one, which
Hmm?
means that we can like predict, or we can
Yeah,
tell
it's
the game what
like
the
a
world looks like.
NumPy seed.
Yeah,
Yeah.
yeah, yeah. We can tell we can use a seed to say what the world will look like.
Yeah.
So that's me back there. Um, and yeah, so 4 minutes 50 seconds just clears the entire fucking chunk. Um, so yeah, I am the maintainer of a few of the most popular seed finding libraries in Minecraft. It's kind of fun.
Nice.
Yeah, and I think of this Discord, about there's like, I think there is 40 records because it's you have random seed glitchless, set seed, and set seed glitchless. Then you have overall the nether, and each of those have 5 categories. I think out of the 40 records, we hold 35 of them. And apart from that, real quick before we begin, I also am the main moderator of Keep Talking and Nobody Explodes.
And
So
then
that's a game where you like blow up bombs. So if you look here, I am yeah, Tatsuya, he left, so I'm the main moderator here. So it's a game where you like have a yeah, you've got like modules and you need to follow a manual to disarm them. Usually you do it with 2 people, but we have learned the manual by heart, of course. Um, so yeah, we just do it. Yeah, we do it by heart. So yeah, and I have I don't have any like I think my full game speed runs are like I've got like I'm 8th place here, which is horrible. I'm like twice as slow as the slowest one. But if we look at level, this is the most ran level.
you only speedrun Minecraft or everything only
And this,
regarding
so
Minecraft.
I am the number one
This is
spot here, which is a 1.5 second bomb. So it begins, click, 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 bam, bam, and that's the bomb. Fucking crazy. Um, but yeah, so I used to have a whole bunch of records here, but
nice.
like they got taken over. Most of them, I'm second or third right now. So yeah, that's what I do with speedrunning, and I'm also the person who like verifies all the speedruns for this game. So yeah, that's what I do with speedrunning. But now that everyone's here, we can probably start the exam again.
Yeah.
So I've looked at this one real quick, and it seems that this is a lot more doable. I think personally, so that's good. So let's start with the first one. What is Moore's law? Let me actually start timing. There we go. What is Moore's law? I'm recording. Yes, I am. Oh, there's going to be many annoying Telegram notification sounds. Sucks to suck. Oh well. What's Moore's law? What's Amdahl's law? So, one, we know these. Moore's law says that every
1.5 years.
1.5
Yeah, 1.5 to
years
2
the
years.
transistor count per square centimeter doubles on CPUs. Right? I believe that is what it says. Just the amount of transistors. And since that is now capped, we are now going to another law which says that not the amount of transistors, but the processing power doubles. I believe. Either that or Moore's law itself is the processing power, but I don't think so. Huh. Well, we might get half a point for this, but like this is also something that I would learn that I'm gonna like learn from by heart somewhere tomorrow, right?
Yeah.
And
I mean, it says something like that, or like I think also on the slide it says something like that the amount of cores on a chip double or something every 2 years.
yeah,
or
the
something.
amount of yeah, I don't know. It's something like that. Amdahl's law
Something like
says
yes.
that if a fraction f of the program is parallelizable, then the maximum attained parallel speedup is 1/f. We've heard this one before. We know the story by now.
Fraction that's sequential, right?
Is
Yes,
A sequential part.
sequential fraction
true.
or serial
So, sequential. So if a third of the program is sequential, then the max speed up is 3 times, which makes sense.
Exactly, yeah.
Good to check that with some what do you call that? Fucking example. Right. What are meaning UMA and NUMA? I actually read this during last exam, so it's a unified memory access and non-unified memory access. So either you have one big memory pool which everything accesses, or NUMA is that when you each have their own small little part of it and you talk to each other. So UMA,
Yep.
unified memory access, one big memory pool which every thread can access. NUMA, non-unified memory access. Every thread has its own little, I mean it's not thread, it's core or processor. Oh well, I'll use
Yeah.
On the slide it says uniform.
Oh yeah, sure, uniform. Same thing really.
I think this question is a bit me. I literally wrote this from the slides, and it didn't seem like the acronyms were that important, so I didn't even write them down. That specifically.
yeah.
They're in there, but I wrote like uniform memory access computer, not like
Yeah.
Yeah.
because it's called a shared memory system and distributed memory system.
And
Even
if it needs, or yeah, its own memory region. So the threads right up to the top will.
do you think they want a bit of extra info, like that they need what do you say? They need communication, where they share their memory, or they might overwrite stuff.
Well, I mean,
Do you think you would want that answer?
I think right now they just ask what are they?
Yeah.
Right. So what's the
Where do you
meanings?
get that information, Tim? Because on the slides I didn't find much other than some pictures.
Well, I remember because I googled it, but
Okay.
other than I think it might have said it on the slides, but I googled it and probably as well.
Right. Okay. So that's that. Hope everyone's okay with that answer. So UMA, uniform memory access, one big memory pool which every thread can access. Non-uniform memory access, each thread has own memory reach, so threads will have to get the memory or get the data from the other threads.
I found it. Write operations require mutual exclusion. That's what it says on the slide.
Yeah.
And for what was that?
That's for both.
Yeah, because if not, you're just gonna have like, okay, I'm gonna read this, and then someone else writes halfway through your read, and you have a dirty read.
Yeah, it's from the last thing where we had like flow dependency, anti-dependency, that kind of stuff.
Right. Let me just check real quick. Yeah, I'm still on the right Interconnect networks can be distinguished into two main classes. Give an example of a network of complexity OP log P for each class. Okay, so what I'm going to say here is for static networks, or for dynamic networks, this is an omega network. There are, I think there are log P lines of P connections. For static networks, this is, so if we're talking about total cost, so let's see, which ways do we have?
I'm also a bit confused by what they mean with complexity. So, but
honestly, I think this is the amount of lines. If I'm gonna have to
amount of
guess,
lines.
I'm not sure.
Yes, the amount of edges that connect nodes.
Yeah. So
Right.
a 4D hypercube has n log n over 2. So that is O of n log n. So that is a 4D hypercube. As this has n or p. If I can, I'll be fancy. I'll use the fancy things. Frac p c dot log p over 2 connections, which is O n c dot log n, or they asked for p log p. Yeah, a mega network log p lines for p connections, for static network for the hypercube. Yeah, O of p log p with another close bracket. Okay, this is again, this is just me repeating facts that are on the slides. Given parallel programming with 4%
Isn't this what the exam is all about?
Given a parallel program with 4% of the code that cannot be parallelized, what is the maximum speed up? So I'll start with the second question.
You
Maximum
said,
speed up
right?
if you have
1 over
infinitely
4.
many. Well,
No, but
so this is 4%, so it's 1 over 0.04, so 25.
Yeah, that's what I meant. 1 over.
Infinite processors, 1 over f is 1 over 0.04 is 25. I could write this with fancy math, but honestly, why would I? 24 processors. So this is actually a funny way to think about it. So you would definitely need the 4%. So 0.04. So what is the maximum speed up? So that's
the upper bound, right? So that's 1 over f, what we stated.
So for the, that's with infinite processors, just do 1 over f. So I'm gonna like logically reason here. So I'm gonna say t. So the speed up is t serial over t parallel. Or hell, what I can even say is so 4%, so 0.95 or 96 times t parallel plus t serial c dot 0.04. Does this kind of make sense? Like, so far we're not even looking at the processors, but yeah. So the reason that this works is because this is also how Admel's law is defined, or because if you have infinite processors, t parallel 0, so this falls away, so it's t serial over t serial times 0.04, so you get 1 over 0.04.
Yeah, this is right, but like you can just, because you can all express it in t serial basically, and then you can take it out, and then it's just 1 over what you put in a way. So it's 1 over like the f plus 1 minus f, like what you put down there in a way.
Yeah, so far I'm just gonna like write it out a bit, if that's okay. So t parallel, if we have 24 cores, is going to be at max T serial.
Oh, you should divide it by the P as well, right? Or not?
T-serial
Do you
over
not divide
24,
it by the processors?
Well, yeah, so that's what I'm currently like doing now. So I'm saying T parallel is at max T serial over 24. I don't think it's exactly the case because you can have like hypolinear stuff, but oh well. So then that would be that would turn into 1 over 24 times 0.60 or 96. Oh, what? Oh, refreshed. Oh. 0.96 plus plus 0.04, and let me just make this a bit prettier. So it's frac 1. So then that turns into so this is 0.96 over 24 is isn't it 0.03? Yeah, over 0.04. So it should be 0.07 if my mental math is correct, which it very well may not be.
I'll just get a calculator if you want.
Yeah.
Are you happy to do it like this?
0.96 over 24.
Yeah.
Yeah, okay, I was wrong. It's 0.4. Haha.
Ah.
So then it's 1 over, which is 12.5. 12.5. So the max speed up is 12.5 times. So yeah, the only assumptions I've made here, I believe, are that the maximum parallel is 24 times the maximum serial. But yeah, for me, that's the only way I see to actually solve this. So I wouldn't be surprised if that was what they wanted.
Yeah. I think this is right.
Yeah, I wouldn't be surprised if it was right. Say it like that. Right, 5. What is output dependency? Right, okay, yeah, so we know that. So output dependency is where the output of one calculation is required for the next one. So we can say for I in range, haha, we're using Python here, fuckers. Then AI is actually be 1, then we don't want to index at 0. AI minus 1 times 2. Is that the case? Yeah, because right now you can't do 2 before having done 1.
That's not what it is.
This is output dependency, right?
This is flow dependency.
Because output dependency is that you have 2 different, in a way, computations that have the same, that override the same output.
Yeah, they override each other.
Okay.
Yeah.
Well, that's what we're doing is with each other. So then you would go, I mean...
Well, you can just say in the next line AI is and something else, and then you're there.
AI... In the next line, AI is something else?
Just the next line, AI is, and then another formula, and then you have an output dependency.
So would this be output dependency?
Yes.
Yeah.
I plus 1 you don't know yet, but I would say like I minus 1 plus 3, and then...
You could also, for example, have like AI is something completely different, like CI plus BI, and then the next AI just something different again, right? It's just the fact that the output is written twice, but with different variables in a way.
Yeah.
If you haven't used it yet, you have a problem.
Yeah. So the thing is, if we split this up, I mean, you could just copy this, that's lazy. If you split this up, this wouldn't cause an output dependency. So yes, you are overwriting the same thing twice, but not from different points in the loop, right? You're both in the same, you're both on I. So you could split this loop up. If you didn't have flow dependency, you could split this loop up and it'd be fine. You wouldn't have.
Yes, but that's the thing of output dependency. You can't split it up with different, like you say, I is 1 to something, and then L is 1 to something. That's the way how you split this one up. That's what it's said in the slide somewhere as well. This one's easy to fix. By just using different loop indicators. Yeah, use intermediate variables. That's what I have in my notes. That's how you fix it.
That's how you fix also anti-dependency, right?
Output dependency, because I don't think they explained it very well. I'm just gonna in parallel computing. Oh, fuck that. Output dependency. Dependency right after right. Okay, yeah, so yeah, it's just like literally you have to wait for the other one. Is there a way that I can put this in a for loop? Yeah, okay, I've got it. So literally what you can just do is you can go CI plus 2 B is, and then AI is B. Bada bing, bada boom, output dependency. Yeah, okay, yeah, okay, this is clear for me as well. Now I actually understand.
In a way, this is now flow dependency, right?
No, this isn't flow dependency. You can if the output dependency was gone, aka this was like this could be split up sequentially with no problem. So yeah, this is this is output dependency without flow dependency.
Okay.
So the multiple threads overwrite the same output, or multiple calculations overwrite the same output. Yeah, that's output dependency with an example. Let me just start a verbatim block so that it's actually readable. There we go, way better. Right, does that make sense? Am I not saying dumb shit? Doesn't sound like it. Lovely.
I'm not sure if I'm convinced yet, but I might just be.
Well, so the thing is, if you do this in parallel, right? So then you have thread 1 and 2 both writing to B, because B is not it's not an array. You don't get your own part of B, you get a single part of B. So, or you get just B. So say that thread 1 writes to B, then thread 2 writes to B, thread 1 reads from B, and then thread 2 reads from B. So then both thread 1 and thread 2 have read the results from thread 2. So, like, yeah, because they both use the same output.
I don't know, like but maybe that's just, I don't really understand maybe, but so for me, I still think that, if it's written like this, it's flow dependency, but I don't know why
specifically, I1 and I2 use the same register to store results. That's not happening here, no?
Well, yeah, it is. B is a register that they use to store results. It's just that the results get immediately used.
But then that B is used to be stored in a different register in A. So is it not with output that, for example, you would have something that stores B, and then the second line is something else that's stored.
No, I get it.
So
yeah.
if you store into B twice in the same thing of the loop, then you don't have output dependency, because, well, you will still have output dependency, but say you have here bi, and then here you have something else like di. So if you have this, then you don't have output dependency, because you can split this loop up perfectly, like with you can be using 5 different. You can be calculating 5 different parts of the loop at the same time without having any issues, right? Because you're each storing to your own little register, bi.
Yeah.
So you might be confused because the reason to write it here, but you should remember that EI and E2 are happening at the same time, and that's the important point. Here they aren't happening at the same time; they're happening sequentially.
Yeah. Okay, I see. Yes.
Lovely. And so the reason that it's here a problem is because this is happening. So this instruction is happening at the same time for IS1 and IS2. So at the same time, they're both writing the B.
Yeah.
And then you don't know which one works. So that's why it is output dependency. And sure, technically, like it isn't storing the result of the entire calculation in B, but it is storing a output, namely the output of CI times 2.
Yeah.
Okay, lovely. What are OpenMP and MPI? Describe the main features of them, the main differences between them. They are, and by the way, what I'm going to be writing could be half bullshit because I've never used OpenMPI before, but I do know them from slides. So they are frameworks used to parallelize code. The main difference is that OpenMP
uses shared memory, right?
Yes, that's one of them. Shared memory and
MPI uses distributed memory.
Parallelize. So the thing is, one parallelizes instructions, the other parallelizes like communication.
Yes.
One has more explicit communication. And
yep. I could not have answered that by heart, but
yeah, because the one inner instructions and MPI uses
explicit communication and synchronization.
Yeah, so I'm not. My wording is incorrect. With explicit communication. Yeah, that's the better way to say it. And implicit communication, non-shared memory with explicit communication. Yeah. This is. I think this is a good description of the two.
It says it in the slide, but I don't even know what the difference would be now with implicit distribution, not communication. But
yeah. I don't know about the main difference between distribution and communication. Honestly, I feel like they're the same because you're both distributing data. I hope this kind of makes sense. What's written here? Because OpenMP, your communication is implicit. So you say you write to a variable and it does the communication for you. And MPI, there's no shared memory and the communication is explicit. You really have to say talk to this thread and do this.
You have to do this message communication.
Yeah.
Send and receive.
Okay, so 7 then. Wait, let's see. What are they? They are frameworks used to parallelize code. I've said that. Given a sequential program or algorithm, which part of the computation should we start to parallelize? The one that is that takes up most of the time, right?
Yeah, I think it's literally that.
Yeah, the part that takes
with for loop
most of the time. Well, yeah. On the one hand, on the other hand, not everything that can be parallelized is a for loop. For loops are a great target.
What you said, the part that takes up the most time, that's literally somewhere in the slides, I think.
Yeah, because like if there's a for loop that takes like a second, and there is a single line of code that takes a minute and you can split that single line of code up into a for loop and parallelize that, then it's better to just do parallelize that part of the code. So yeah, I feel like if I had to parallelize a program, I would run a profiler, find the most used code, and parallelize that.
Yeah.
Because the question is literally, which part should we start to parallelize? So I do agree that for loops are easy to parallelize, but which part of the computation should we start? The one that takes most time. Can we use the same approach to parallelize Jacobi iteration versus Gauss-Streidel?
Well, this is lecture 7 again.
Yes, and the answer of the previous question answers this question, I believe. So Gauss-Streidel, you cannot. No, because GS uses data from the current iteration, while Jacobi only uses data from the past iteration. Yeah, so this was what was in the last slide, and that's why how they said that you can't do this. So, is this correct? No idea. But I mean, it is.
You can check that with the lecture slides of L7.
Yeah, we'll check that later. What is diameter? Oh god. Okay, what is the diameter and bisection bandwidth of an n-dimensional hypercube network? I'm gonna try to answer this, even though I haven't memorized it. So, the diameter is pretty easy because you use this in Hamming codes. So, say you have a two-dimensional hypercube, then that's also called a square. So to get to the other side, that's a distance of 2. If you have a three-dimensional hypercube, which is again just a cube, then the main distance is 3, because you would have to walk past the square and then up, or like, yeah. I know it's difficult to explain, but with n dimensions, the furthest you can walk is n. The furthest that 2 points can be apart. And I have a beautiful proof for this that I know from a 3 Blue 1 Brown YouTube video. But I'm not going to go into it completely. Does this like make sense that the diameter of an n-dimensional cube is n?
N.
N.
Yeah, it's just the size of the edge, right?
Yeah. So, say you're at one point and you want to get to the complete opposite corner. You have to walk n distance. Okay, I'm gonna.
It's the diagonal thing that we.
Yeah. So I'm gonna quickly fucking I'm gonna quickly write down a proof,
but
because I fucking love this proof. Okay? So
wait,
you can describe
the furthest. What does diameter mean again?
Diameter is the farthest that 2 points are apart, if I recall correctly.
Yeah, the longest path or something.
Yeah. So on a hypercube of n dimensions, you can describe a point.
Hypercube is just a cube, right?
A hypercube is a cube that goes to higher dimensions. So a hypercube in 3 dimensions is a cube.
I just think of it as a 3D?
Yeah, sure. So you can describe every point by which side it is on one axis. So if you have a cube, then so say you have a cube where you have like square, bit of lines, bada bing, bada boom. So where this is up, this is right, and this is back. I hope that that visual makes sense. Then you can describe it. You can describe every point.
You're recording, by the way. Yeah, you are. Are you recording?
Yes. My boyfriend told me, but thank you for telling me as well. So you can describe every point by where, or by like 3 coordinates, where every coordinate is just it's just that a coordinate. So this would be 0, 0, 1. Yeah, good enough. So and this far back point would be 1, 1, 1. Does this make sense? So this is the second coordinate, this is the first, and this is the third one. So this will also scale to multiple dimensions. So if you have 4th dimension, you can describe it with 0, 0, 0, 0, and the furthest corner would be 1, 1, 1, 1.
Yeah.
And to go from any point to any other point, you just have to, because you can always swap one of these coordinates to the other one by walking past an edge. So say I want to go from 0, 1, 1 to 0, or from 0, 0, 1 to 0, 1, 1. That is just switching one coordinate, so we can do that in one step. You would go here, so this is 0, 1, 1. And you can do that with one step. So say you have to go to the very opposite side of a cube. You have to just change every single one of the coordinates once. So say from 0, 0, 0, I need to get to 1, 1, 1. I need to swap one of the coordinates. So say we swap the first one, then we're at one, then we're at I wrote this wrong. This needs to be 1, 1, 0. So say we swap the last one, then we're at 0, 0, 1. Then we swap the middle one, so then we're at 0, 1, 1. And then we swap the first one, and we're here. So you can always get to the other end by swapping all the coordinates, or all the coordinates of that point once. And you can do the same. So you can always, for n dimensions, get to the other side in n moves by just swapping all the coordinates once. And that is why a n-dimensional hypercube has a diameter of n. Yeah, lovely 3-room round video about that. Bit of a tangent, but it's fun information. So yeah, diameter of n-dimensional hypercube is n. Right. Then the bisection bandwidth is the amount of links that you need to remove to get to a completely partitioned networks. The nice part about an n-dimensional hypercube is that it is that every n-dimensional hypercube is just two n-1 dimensional hypercubes glued together. So say you have a normal cube that is just two squares glued together. If that makes sense, right? So you can just cut these 4 lines, and then you have the 2 cubes again. Oh, I need to continue the timing. So for 2, the answer is 4. For a for a 2-dimensional hypercube, also known as a square, you can cut 2 lines to get 2 you can cut 2 connections and get the line back. If you have a 3-dimensional hypercube, that's 2 cubes where all the edges are connected to the same edge on the other cube. So that's 8 connections. So I think that so 3 is 8, so it is literally just 2 to the n. So the bisection distance is the bisection width is 2 to the n. For my very limited sample size. But it makes sense, right? Because every n-dimensional hypercube is 2 n-1 dimensional hypercubes, where every point on that cube is connected up. So the amount of connections between those 2 cubes is the amount of points in an n-1 dimensional hypercube. And the amount of points in an n-1 dimensional hypercube is 2 to the n. I might be going a bit fast, sorry.
Yeah, I don't know. Like, I'm looking at the slides at the same time, and there it says 4D hypercube. The what's it called? The diameter is log n, and then the bandwidth intersection is n over 2. But it doesn't really say how it gets there, or
so
just
let's see.
Cubes, and then
The
it just
diameter. Oh yeah. So this is because I am using n wrong. So n is not the n. I'm using n as the dimension.
And it's number of
dimension, but it should be the number of nodes. So
okay.
Yeah. Okay. So my question was correct, or my answer was correct, but the question was wrong. I was answering the wrong question. Good catch. So this wouldn't be. Yeah, the diameter of an n-dimensional hypercube is n, which is correct, but the nodes in an n-dimensional hypercube is, I think, n plus 1, n plus 2 to the power n plus 1. Yeah, so that is it. Fucking hell. To the power n plus 1, which is not going to accept because I'm not actually writing LaTeX. So, and this is because, this is just reasoning, right? So if you have a a cube has 8 points, so that's 2 to the. Wait, no, is it n minus? That's right. Cube has 8 points, and it's 3-dimensional, so it's 2 to the n actually, for points.
It says that the diameter is log n and bisection n over 2, huh?
So,
for n being...
Yeah, so that makes sense, right? Because the diameter of an n-dimensional hypercube is n, but we're not talking about the n dimensions. We're talking about the n nodes. If you connect the nodes to the diameter, so nodes n diameter nodes 2 to the n gives diameter n, but we want to express this in terms of nodes. So nodes n gives diameter log n. So this makes sense, but it's not. There are better ways to approach this. I'm sorry, but yeah, nodes n gives diameter log n, and we also have the bisection distance is. So let's see, what was it? So, and bisection direction of n-dimensional hypercube is 2 to the power of n minus 1. So that means that nodes nodes 2 to the n gives bisection distance 2 to the power n minus 1. If we copy that, we can take the log of this. So nodes and bisection distance. Is this correct?
It's a bit small to read right now. So
yeah, fair.
Really.
Bisection distance is n over 2. Now that makes more sense. Yeah, because it's half of the nodes. So yeah. But I'm wondering where in my logic am I going wrong? So
maybe it's just then because it's just because we have to relate it to the dimension, I think. So it's like you have the nodes. That's one thing. So that's like if you would say it's 3-dimensional and you would have sort of have a cube, you would have to say 8 points. And then bisection, so that's half of it, so 4 points, so n over 2.
Yeah.
Then relating that to a 3D dimension, for example.
Yeah, so, I mean, if I just work about this in the amount of nodes, the amount of, with nodes n, because like I said, dimension n gives, so 2 to the n points means that you have to cut 2 to the n minus 1, so a half 2 to the n. So yeah, nodes n, bisection distance, n over 2, which makes sense with what I said, because you need, because it is 2, so for a n-dimensional hypercube, it is practically 2 n minus 1 dimensional hypercubes glued together. So the amount of stuff you would need to remove is the amount of nodes in an n minus 1 dimensional hypercube, and that is n over 2, because it keeps growing with the square, or with a power of 2, which is a very contrived way of getting to this answer, but I think it's correct. Luckily, they don't ask for an explanation; they just ask for the answer. Do they? Yeah, no, they just ask. Okay, yeah. So bisexual bandwidth and diameter. So yeah, I hope I didn't lose you all too much, because I went in a bit of a tirade, but I think the answer is correct. Lovely. Describe communication time as a function of message length. Okay, so that is startup time plus communication bandwidth. No, not bandwidth. Throughput times message length. right? This would be the formula for this, I think. I don't know if they're asking for something more like clear, but yeah, the communication time is always just the startup time plus how many bits you can send per second times the amount of bits.
The formula describes communication time as a function of the message length.
Yeah. So
Yeah.
startup communication time is startup time plus communication throughput times message length. Where startup time is the startup time communication through. No, I'm not gonna fucking type that. They understand what this all is.
I think this was also a question in the lab somewhere, like in the MPI exercises.
Maybe specify parameters or constants and variables in that formula.
Yeah, sure. So startup time is the constant startup time that has to happen for every message. Communication throughput is the amount of time it takes to send a message in bits per second. Message length is the message length in bits. Look at me being all explicit. And I'll add even here in seconds. And then communication time is the... No, okay, they don't ask for that.
Yeah.
Right, okay. So, what are data parallelism and task parallelism? Data
parallelism we described in the last exam.
Yeah, so data parallelism is splitting up a given bit of data to between threads where every thread gets its own chunk of the data. Task parallelism splits up the tasks that need to be done on data where every thread gets its own task to perform on the data. So say like you have a function where you need both the results for n squared and n to the third, then task parallelism would say, okay, one thread compute n squared and another thread compute n to the third, and data parallelism would say, okay, for this range of inputs, this thread gets to compute n squared and n to the third of this input, the other thread for the other inputs, etc. I believe, anyways.
You compile it?
Sure.
So it's easier to see what you you wrote.
Yeah, fair.
Data parallel splitting up, give me data, splits up the task that needs to be done on data, where every thread gets its own task to perform on the data. Yeah, that makes sense, right?
Yeah, that's what I was hoping, yeah. 12, consider the following.
Next question.
Independence from A and D. Can we use parallel for...
Nope.
So B and C are independent from A and D. So B and D or B and C are just like B and C are independent. So these are just constants practically.
They're basically only reads in the memory.
Yeah. So practically you need to have the... So because we're setting A plus 1 and then using AI, but we're also using D plus 1.
Yeah.
So because this D plus I is being reused, we have a flow dependency, I think.
Or anti-dependency.
Well, yeah, because it's not going up, it's going down. Yeah, so this is indeed anti-dependency. So this is just data that gets overwritten by...
No. I'm not sure if it's anti-dependency because there's no risk of DI ever...
there is, if you split it up.
If you parallelize
if you parallelize it, DI would be split up. So That's an anti-dependency here, and here we have just another anti-dependency.
No.
We set a plus 1 and then produce a. So yeah, a plus 1 depends on a, so that's a flow dependency.
Yeah.
Yeah.
I think so.
No, because there is a flow dependency on a and an anti-dependent.
I don't see the flow dependency.
D.
I don't know why you say that A1 depends on A0, for example.
So,
It's just an X1.
so
Right.
A1 doesn't depend on A0, but A1 depends on task, or I plus 1 depends on task on task I. So you can't perform task A plus 1 without having done task I.
You can't perform I equal 1 without performing I equal 0 first.
Exactly, and that's flow dependency. Give a solution so that the loop can be executed in parallel. Just real quick, how long do we have for this? 3 hours. Okay, Leo. So for this one, we can simply copy our own version of D. So so this is using OpenMP. That's good. I wouldn't want to do this in MPI. So let me do a begin verbatim. Let me just, there we go. So pragma OMP parallel for and then we say that if we do private D, I think that will, like, does private D distribute a copy of D to every single thread? Like if D is already instantiated?
Not sure.
Google time.
What did you say?
I was wondering if the private pragma, so the private annotation, if that's, so say we say here D is 1, 2. Just for fun. Does each thread now get their own copy of D with 1, 2 in there?
Yeah.
So the data gets preserved with a share, with a private. Okay, so then the anti-dependency is fixed now. So as for this, because a plus 1 gets set by because a plus 1 gets set by everything, or a plus 1 gets set by task I. So I somehow feel like we should just be able to do this as long as we start 1 bit later.
Wasn't it not that he said something that if there is flow dependency, that you can never parallelize it?
Yes, so I don't think it says flow dependency per se. Because that's true.
You can by writing it differently, but flow dependency, I thought he said that's just not possible.
Yeah, I have that in my notes, but I don't think that's what's going to happen here. So maybe this is actually not flow dependency then.
Yeah, maybe not. Maybe it's just anti-dependency, because then you can, by creating a temporary, array and then just naming it that.
Flow dependency is like when we use a time iteration in the finite volume method, for instance, and we need the previous view for our next view, and you cannot go forward, but that's not happening here.
Yeah,
because
so you don't need data to be. So the thing is, you don't need data from the previous calculation. You just need the previous calculation to be done.
I think it's both anti-dependency then. AI plus 1 is
so
because we're overwriting.
Sorry.
I think it's anti-dependency because we're overwriting AI. However, we do not need a previous AI, for instance, to calculate DI. But we should not overwrite AI plus 1 when another parallel construct has not used it yet, if I'm not going too quick now. So if you same here, if you copy AI and just first let's say you first use it in DI and then you overwrite it with AI. It's already fixed, right?
Yeah.
more
So I do think that if you so if you had an extra array, so say for example E, and then you say I plus 1 is this thing, and then hell, I believe E can even be shared. Shared E. And then we calculate E here. And then afterwards, after this is all done, we can do pragma. I mean, we can parallelize that. Is it even necessary? Just for, you can just copy this.
I just simply wrong and can't we parallelize it? But
AI is.
Might do if because he doesn't give any hint that it's not parallelizable. So if he does this in the exam, I'll be a bit sad. I hope if it's not parallelizable, he says,
No,
or
no. So
is this
this
not
absolutely is
parallelizable?
parallelizable. So my question was more, is it if it's not flow dependency, is it anti-dependency or is it just a type of dependency we don't have a name for? Because it is not data that we're dependent on. It is like something being executed before it. So it's not a data dependency. It's a time dependency almost.
we maybe just split the loops into 2 loops.
Yeah. So I think the way that I've done it here, it should work. Let me just recompile. So instead of storing it in A plus 1, we store it in E.
Yeah.
And then by the end, we're copying E over into A.
Then
But I think this is going wrong because we need. I think reading it again, we need the previous AI. Like we calculate AI one ahead, but we do need the previous one we calculated in the previous loop iteration. So
No.
So I
So
was wrong.
the thing is, because we are, so because we're always calculating ahead.
Mm-hmm.
Hold on, let me actually think. No, I think you're right. Because
So we
AI
can
here.
literally split them and make 2 separate parallel regions. No. First AI and then DI, for instance.
AI plus 1.
Maybe it's not the best way, but anyway.
Yeah, I mean, it'll work. They ask for a working version. I am then wondering about like.
He's not explained anything about how to do this though. Like, so it's sort of like.
Well,
it's a bit.
Yeah, but at the same time, that's what all the labs were about.
Yeah.
So we first calculate the entirety of AI, and then we calculate the entirety of DI. But the problem is that.
That's not the best way, but.
Well, I mean, no. So the problem is that right now we're not in the end putting DI back together. So.
What do you mean?
We are recalculating DI, and then every thread has its own version of DI, and we're not putting it back together. So I think even what should be done is this should be E is D.copy. I don't know if that's a method, but it is now. And then we go E, D plus 1.
So we're copying D to like a temporary array.
Yeah.
We're calling it E. Yeah.
So then then this is just always the old version.
Yes.
And then we don't have to like recombine D in some weird way, like we would if we shared E.
Yeah, I think this is good.
Yeah, I think this will work.
Yeah.
Yeah, because there's absolutely no dependency here, and there's also absolutely no dependency here.
Yeah.
The only question is, does it give the exact same answer? So here we have. So for everything, we're calculating the next. Yeah. So this is exactly the same. Yeah.
Maybe write as well that you called BR or like what you called what.
Mm-hmm.
So you make a copy to an array.
Oh, actually, so give a solution that the loop can be executed in parallel. So we can't split this up into 2 loops. That's kind of annoying. So what we can probably do... No, we can't.
Maybe there's not really a problem with that first line, I think. Because in a way, yeah, you're using you're using
So
this and the
this line isn't the issue. The line is this. There's two issues in here. One of them being
Maybe I think you have to use private eye first of all with
well, I think
right?
I think four
In
four.
the labs we were always using.
So 4 takes this takes the loop variable and privatizes it, I believe.
I don't know. In the labs, I was always writing private eye.
I was as well, but that's just because it's safer. I don't think it hurts. We can do it.
And maybe if we use the reduction clause or whatever it's called, that one does something with this A, for example, but I don't remember with D maybe.
So reduction will just reduce it. So you can't reduction doesn't copy it over; it reduces it to a single value. So you can use sum, you can use count, you can use average, but we don't want.
But he's gonna make a bunch of copies, and then in the end, he's gonna add them together, right?
Well,
that's what reduction
I think reduction. What it does is you do calculations on the whole thing, and then in the end, you reduce it back to one value. So that's a way where you don't have to do some extra shit on your own. At least I believe that's what it does.
That's why we used it on when we did a whole thing and then summed stuff.
Yeah. So for sure we can fix one of these things by just going esd.copy and then putting this in here. So that's one of the two issues fixed.
Yeah.
So let's think about why the other one isn't. So the d.copy fixes this part. So the problem here is that say you have two parallel programs running at the same time, then AI plus 1 might not have been changed yet.
Does that matter? Because
yes, because you're using AI.
It matters.
So if we're running I is 0 and I is 1 in parallel, then AI plus 1 needs to be ran before AI.
I don't know if it matters because let's just call it A1, and then on the next line say the A0. So let's say these two are being done at the same time. So let's say A1 is not yet computed, but then we do have A0 already. So it doesn't mean
what you're thinking about is having these two lines be done at the same time, but that's not what's happening. What's happening is that this line is being done twice at the same time at two different iterations. So at I is 0 and I is 1.
A1 and A2.
So
if make the second line plus 0. 1 and plus 2. The I plus 1, AI plus 1, EI plus 2. Then you don't have the problem where on every first iteration where the loops split the arrays that you take the wrong that you grab one wrong part of the array. You know what I mean?
But so let's
because the issue is
let's say these two lines, if they are parallelized, then it could be that, for example, one is done before the other, right?
Well, sort of, but that's so the issue isn't one being done before the other in the same iteration. The issue is that we need to run this line for n is 1 to be able to do this for n is 2, right?
Mm-hmm.
Well, that's what I'm not sure about, because AI, we have that already.
No, we don't.
Right?
So we don't. For I is 1, we don't have AI yet. We have a old version of AI, but we need I is 0 to compute this before we have the right version.
Are we not using the same there for the
so
AI? We're using, in a way, well, it's AI plus 1 is overwritten, but AI has nothing to do with that, right?
So the thing is, so say you have a value with a, and that starts out being all zeros, right? And here you set it to some other value than 0.
Yeah.
Then if you are running A0 and iteration 0 and iteration 1 at the same time, and you run for iteration 1, you run this before iteration 0 has run this, right?
Yeah.
So then you're working with AI, which is 0. Because it hasn't been set yet, right? A1 is 0. But what we need is iteration 0 needs to compute this, which puts another value in A1, and then this isn't 0. So the fact that this value gets updated by another iteration, which we do not have control over, that is the issue. You don't want this to be the value that it is at the very start. You want this to be the value that we will compute for it in the previous iteration. And that's why every iteration depends on the previous one.
Okay, yeah. I see what you mean, but parallelization will be done within the loop, right?
No, absolutely not. So say you have n is 10, then parallelization will be done by giving one thread I is 1 to 5, and giving another thread I is 6 to 10.
Is it always like this, or could it be 1, 3, 5, 7? Like
so it depends how you do it. If you do OMP parallel for scheduled static, then one will get 1 to 5 and the other will get 6 to 10. If you say dynamic, it will get 1, 3, 5, 7, 9 and 2, 4, 6, 8, 10.
Is it? I understand this. If you put static, then it's 1 to 5, 6 to 10. But the dynamic, is it always even and odd if you parallelize twice,
so
or is it?
So you can.
The moment one finishes, it gets the other one. So if
you're
two
right,
finishes
yeah.
before
So,
one, then who's gonna get 3?
3. You're right. No, you're right. I said it wrong. Yeah.
Okay.
No, yeah, completely right. I believe what I was talking about is static, but the chunk size is 1 instead of length over.
Yeah, with the chunk, I don't understand anything.
So the issue is we don't have AI for each first iteration, but we do have AI plus 1.
Yeah. So indeed, something we could do is we could. What you were talking about is this, but then there is an issue where we have to say
we're running out
of
our arrays.
I is not n or n minus 1 minus 2 actually. Do this, and at the very beginning we have to say D0 is A0 plus E1. So because we are moving this forward, one calculation will be done less. So we are like the last calculation we don't want to do because they'll reach outside of the array, and the first calculation doesn't get done, so we want to do that at the start.
Why are we using E again?
So E is because if we're not using E, we are updating D and then still using D, because here we are using D plus 1 to calculate D, or D plus 2 to calculate D plus 1, or DI plus 1. So if we execute 2 before we execute 1, D will be wrong.
Yeah. Then you get nasty overlapping.
Yeah, exactly.
Yeah, gotcha.
So I think that this is a thing which allows the for loop to be parallelized without causing issues.
Okay, yeah.
Yeah.
Sorry, never mind.
No problem. Yeah. So I think the names here are wrong. The anti-dependency and anti-dependency. I think one of them is wrong. I'm not sure which one. I don't have the brain power to think of it. But this code should work and it should adhere to their standards. 13. What does false sharing mean? False sharing is sharing a chunk of data which constantly gets updated so that what do you call the buffer again that they're using? It's a cache, so the cache, so that we can't use cache to retrieve it, and we'll need to get it directly from memory, which takes way longer and reduces parallelization efficiency. I hope that makes sense and I'm not spouting bullshit.
It constantly gets updated so that we can't use cache to retrieve it, and we'll need to get it directly from memory.
Yeah, so it's like in so it's in like, say we have a for loop and we're adding up a whole bunch of values, and we're writing, instead of using like a partial like a total for this thread, we just have one global total. Then every time a thread changes that, then the other threads have to wait for it to be done changing it, and then have to get that new value from memory because it's not in their cache anymore, and that means that we're all practically waiting for one thread again.
Okay.
That's what false sharing is, I believe. And this is... Yeah, how to modify to prove... So, yeah, this... Actually, isn't this exactly fucking code that we had to solve in the Pi thing? So the issue here is that the entire chunk, the entire, like, cache block, which spriv is in, will get modified every time, so it gets so the cache gets dirtied and it has to be regained from memory. So the best way to do this is, or the way I did it at least, in my exercise. Oh, don't sue me! I'm sharing exercise answers. That's actually a pretty big fucking deal in the computer science Discord. We have like a whole thing where we have an emote of a guy who would like be the one to get you for fraud, and every time someone shares code, we send that fucking we send that guy in there. And his name is. And honestly, it is very easy to commit fraud with code. Like, you're like, oh, can you guys help me debug this? And you send your solution, and then everyone can copy your solution. It's like, you don't want to do that. But yeah. So, what I loved about this way.
You do that all the time with Earth Sciences, I think.
Very possible. It's just like, and as that's also why there's such a like pressure on it on the computer science department, because yeah, like you don't want people to just steal each other's code.
I mean, it's more of a deal for us. It's just to learn from each other, I guess.
Yeah,
right?
I mean that works, but it might not be what they want, and especially if it's graded, that's an issue. If it's not graded, generally they don't care. But if it's graded, they're like, don't do that. But yeah, one of my favorite parts of this is, so the way I did this, and I think this is just really funny. You just do this, and you go reduce. S semicolon space plus or reduction, and we'll call this total, and we go float.
I tried real quick here trying this.
Is this question 4, by the way? Like, is that what?
This exercise that we were doing before, trying to parallelize it. I don't know.
This is exercise. So in the test, this is exercise 12, and this is exercise 4 in the for the OpenMP. So please don't kill me, Mr. Parallel Teacher. But you asked for the fucking question.
Back to that question that we were
this one?
discussing before. Yeah. No, I don't know what's the right answer, but I just tried out without so in serial with some random arrays.
Yep.
And I got an answer. And then if I just do pragma OMP parallel for private I, it gives me correct answer also. So wondering.
So the thing is, these are not things that will go wrong for sure. They can go wrong. Because it depends.
Yeah, but I ran it like 100 times.
So the original thing you're talking about? No idea. Maybe the thing you're running on only has one thread, or maybe you didn't do export set threads. Did you do export set threads?
It should definitely go wrong on the edges
that's
of
my
the...
mistake.
Yeah, you're right. It should definitely go wrong on the edges, because you will never do the last one in a field before. Huh. Weird. Well, we use logic to deduce ours anyways. But yeah, like, I believe that this one should work. Yeah, because so what this does here is it uses a single variable as local, so this is not false shared because it's never shared anyways. I mean, maybe I can do private total if we want to be sure, but I believe everything in reduction doesn't get shared. I think actually that you shouldn't do this, but yeah. So it uses a single variable as local thing, so there's no caching here going on, and in the end, total will be added up and put into total. So the total of all the threads will be put in there, and we're done. So I believe that this is a way to do this. Oh, I should probably put parallel here, I think. I'm not sure. I think it's pragma on parallel 4. Yeah, because otherwise you never start dividing it into parallel sections.
Yeah.
Okay. Any questions or any like remarks or objections about this code?
I think this is what we had to do exactly also in question 4. Yeah.
Okay, the execution time of parallel is, oh god, here we go again. Scalability is v increases. This is literally, okay, sure. Yeah, this is one-to-one the same fucking question. Yeah, even with the fucking first term that's divided by p and the second term that's multiplied by p. Bastards. No, right, this should be easy. So we multiply, so it's the overhead, I'm just going to do this by heart. Overhead is n squared p squared, because that's p times tp minus t1. Yeah, so overhead is overhead is n squared p squared. Which is because you multiply this by p and you get n to the 4 plus n squared p squared, and you remove n to the 4, so you just get n squared p squared. And then what we want to know is the ISO efficiency, which is overhead. ISO efficiency is overhead over... was it number of cores or something? No. Workload.
Over the workload, yeah. Hey, what was the workload in the question again?
N to the 4.
N to the 4.
So,
oh, yeah, okay. Yeah.
So ISO efficiency. The numbers were way better here. I like this. P squared over n squared. So if p increases n or by a factor a, n has to also increase by a factor a. Which makes sense, right? I'm not doing anything completely out of the ordinary. I get the workload by, or I get the overhead by multiplying by p, so we get n to the 4 plus n squared p squared. Subtracting the workload, so that's n to the 4, so we just get n squared p squared. And n squared p squared over n to the 4 is n, or p squared over n squared.
Yeah, I have the same, so...
Okay, lovely. So p squared over n squared. If p increases by a factor a, n has to also increase by a factor a.
Yeah.
Okay.
Yeah, makes sense.
Lovely. Then what's the scalability of this algorithm? Scalability is constant. Then.
I don't know what you have to say there. If that's...
Yeah, I mean, I'm not sure either. So they say, in other words, if p increases, how fast must n increase? And I said, if p increases by factor a, n increases by factor a. Can we keep the computing time constant? Yes, we can keep the computing time constant, since we can always scale p squared n squared to be the same. Which is a very bad way of explaining it, but I hope it makes sense.
Hey, but for that question, to keep the computing time constant, we need to look at TP, right? Or
so
else the other thing is if you keep the efficiency constant. That's what
yeah, that is true. Can we
I think if A0 over W you need to keep constant.
If the program size n is increased, can we keep the computing time constant? So say this increases. So because
increases linearly with n, from what you wrote down. I wasn't writing with you, but
no, I wrote down the
efficiency,
overhead,
right?
and the, oh god, it really doesn't like this. I'll be nice. I'll put it in fucking code blocks or in math blocks.
I just want to say that I ran my code many times and it worked, huh? Just with private eye. Nothing fancy.
as it was.
Yeah.
Are you sure there's no like overlapping bits where it's 0, for instance? Like if you make a first 0, then you run it, that there's no zeros anywhere. Or at least
I make
like
a all 0?
Yeah, if you at first just begin with make a 0, because otherwise you're using the a from the last iteration and it doesn't make sense. So you have to clean a first and see if it gives the same output.
I don't understand what you want me to do.
Well, if you, I don't know exactly how you're doing it, but if you run it a second, third, fourth time and you calculate exactly the same, then your A
Mhm.
is gonna be already been calculated by the first one, and then it's gonna be okay. I think or should be at least the second and the third time. But if you start with um,
We have to increase p by a factor p over 4 to cancel out the first term, but this will only increase the
Well,
second
chat the whole
term.
code if you want to try yourself.
Okay, so if problem size increase, what happens to the parallel efficiency in that case? The parallel efficiency goes down. Right. So let me just recompute or recompile. So overhead is p, ISO efficiency is overhead of workload, so that is p squared of n squared. If increased by a factor a, and has to also increase by a factor of a to keep constant efficiency. We can't keep computing. We can't keep the computing time constant, because if we have the workload, or if we have the parallel efficiency here, the first term, to cancel that out, we need to increase p by a factor n to the fourth. But if we do that, then the second term just explodes. So there's no way to cancel that out.
As the other
Same thing as last time, exactly.
question, right? Like efficiency goes down because we have to up the processes to keep up with n.
Yeah. Okay. Now time for the two questions where I'm gonna just fucking take a fat L, namely the red-black ordering and all that garbage. Consider the computation of a discrete 5 point. What's the reason? This is literally the same question, one to one, the same.
So we have to read all that text.
So for the first one, we can just copy our answer from our mind, which is why are we using? What is the reason? So since what the thing is, since GS relies on calculations from the current iteration, red-black black ordering is used to divide the tasks up in such a way that this dependency can be negated by calculating those parts first. In a 9 points, also with diagonal neighbor or grid pairs different stencil is used to discretize it. Can we still use red-black ordering to parallelize the ghost road iteration? So I believe with red-black ordering, or the whole point is that so say we have this matrix. Say we have this funky looking matrix. I'm not gonna even fucking finish it. I'm lazy.
Sorry, let's think about that exercise. You need also the reduction clause. With the reduction and private eye, now I get all the same. Before, when I parallelized with 4 threads, then I was getting different results, but now
with the reduction,
I
it's
am
good.
not. With just reduction and private eye.
Okay.
Really okay.
So yeah, again, so say you have all these points. So I believe the way it works is to do this, to calculate this thing, you need everything around it. No.
Well,
okay, honestly, I could try to explain it. I do not understand this well enough to even try to explain it. I'm just gonna spout bullshit.
Yeah, I have
what is the exercise?
So
15?
the 2D Poisson equation describes the 5-point differential. So this one we just know because that was in the last question. So namely, we can recompile so you can see it. Since Gauss-Strudel or whatever it is, Gauss-Seidel relies on calculation from the current iteration, red-black remains used to divide the tasks up in such a way that this dependency can be negated by calculating those parts first. So yeah, there's that. Then the next question is a 9-point grid, or difference stencil, is used. So not just the things
Mhm.
to the top,
But then
bottom,
I
left,
don't
and
think
right.
this method works, right? Because this
I don't
method
think it
divides kind of.
does, because
Yeah, it
you're
doesn't
also
look
using
like.
stuff from not just the current iteration, but also the next iteration.
Yeah.
So that would be my answer. No,
Yeah, I
since
agree.
you're not just using data from the current iteration, but also from the next iteration. Dot. Okay, am I correct? I don't know. Is it an answer? Yes.
We have
Give.
no way of checking it.
Yeah, that's true. Given a tridiagonal matrix, consider the Gaussian elimination algorithm for solving a tridiagonal system. What is a maximum speed up that can be obtained?
But that's the thing that was someone put in the chat as well, is because that the Gaussian over this this matrix like this can only be done sequential. Then
Yeah. So.
Cannot be done like parallelized.
Yeah, because like every time I believe the way it works is every time you go to the over the diagonal, you iterate over the diagonal, and every time you perform calculations for everything under the diagonal, but there's only one thing under the diagonal, so not much changes.
And in each of these steps depend on the other.
Yeah.
So that's why it comes.
Since there is one number under the diagonal, we can only, or there is only one calculation to be done per iteration, and we can't parallelize a single calculation. Also, all concurrent or all future iterations depend on the current also an iteration depends on all the past iterations. So we can't parallelize that either. This gives 0 speed up. Recursive doublings introduced to increase the parallel speed up. What are the main ideas and price? So.
Okay, recursive doubling, it increases the complexity because basically what you're doing is the.
You're like rewriting the calculation, right?
Yeah.
Doubling.
The nice thing is that you can parallelize it because now the steps are independent of each other.
Mm-hmm. Doubling increases the computation cost.
Is a lot more.
So the total amount of calculations done, but in return it also increases the parallelizability. I'll always love writing that word.
No, it feels like you get stuck in it.
Yeah, explain the main idea and price paid. The main idea is rewriting the
idea is that you have those with that band where you have like 3 diagonals next to each other, right? That's the
the off diagonals further and further out.
You're
out by.
You have the equations, and then you use the I-1 equation and the I+1. You minus that off or something, and then you basically get. You can zero those. Something like that. Go to the slides.
Yeah, no, it does make sense because if you add up the I-1 and I+1 equations, then the field or the numbers in I-2 and I+2 remain. But the other ones cancel out.
And then it says even, I think then that could be the next step where you use the I-2 and the I+2.
Yeah.
Get rid of those as well, and in the end you just have a one diagonal line. But so it's a lot more complex. But then the advantage is that you can parallelize it.
Yeah. Okay. Honestly, I feel like what we can do is we'll just check the answers by just googling the questions. So what is Moore's law? Number of transistors on a microchip will double every 2 years. So it's not one every 1.5 year, and it's also not per square centimeter. It's per microchip and per 2 years.
No.
The
Yeah.
book says 18 to 24 months.
And the
So
book
it's fine.
says 18 to 24.
It's definitely per like area, not per chip.
On the
Indeed.
slides it also says per chip.
Okay. But I remember in the book it says for between 18 to 24 months.
Okay, well
Yeah.
then we're right. Doubles. Number of transistors in an integrated circuit. So in one chip. So it is chip. Okay, so minor mistake there, but whatever. Amdahl's law. We just have this right? This was in the previous exam.
Yeah.
Let me just grab the slides for the UMA and NUMA. Numa. Where is the slides? Yeah, so this is UMA, where everything has one. Well, okay. This is not exactly what I wrote down. I said there was one. Well, yeah, I said there's one big access or memory pool where they all have access to, which I believe is how you could see this, right?
Yeah.
I mean, I love that the slides just have this one picture and sort of like, ta-da, this is it.
Yeah, and they just don't have any other thing explained. Yeah, and here it
Nothing
is.
else explained.
Every processor has its own bit of memory, so you have to talk to the other processors to get the memory. Oh, by the way, time. So yeah, I think that one we have correct. So each thread has its own memory region, so the threads will have to get the data from other threads. So that's what you see here. Like, you have to like talk to each other.
Kind of self-explanatory if you know what the word means.
Yeah. So 3 question was.
Oh, wait, can I go back to question 1 because we concluded every 2 years, but I have the slides for me right now.
Well,
it
we
is every
concluded that 1.5 to 2. In the book, it says
sorry.
18 to 24 months apparently.
Okay.
Yeah.
So I guess there's different interpretations.
Mm-hmm.
But yeah, good to check. So here we have interconnect networks. I give an example of a network of complexity P log P for each class. So dynamic networks have an omega network, log P lines for P connections. Let me just check that, but I'm like 55% sure that's correct. That is... God, I'm fucking missing it. There it is. Yeah, so omega network, there are 2... Oh no, that's switches, not fucking... Yeah, so there's stages, log P, switches per stage. Okay, so... Yeah, I wasn't completely right. It's P over 2 switches per stage, not P.
But I think
for the hypercube question?
No, for the...
You go up for this one, in this this lecture, the one that... So the omega network, what is that again? It's part of like a...
That's the static network, or the dynamic network.
Dynamic network, but what is it called again? What the omega is an example of? Multi something, blah, blah, blah.
The omega is an example of a dynamic network.
Multi-stage network.
Yeah, it is multi-stage.
A multi-stage network is P log P.
Well, so it's O P log P, right?
Yeah.
Yeah, so it's big O. So that's my mistake. So the only mistake here is that I said there are log P lines for P connections, where it's log P over 2 lines for P connections.
Yeah, true.
Or no, it's log P lines for P over 2 connections, because if we go here, we see that the switches per stage is P over 2. Also, I said switches, not lines. Doesn't matter. I guess the cost is the switches and not the lines between the switches.
I think you're right, though. I think the omega network is because it's like order. So
it is the omega network for sure. It's just that my calculation on how I got to the O P log P is the issue, because I thought that the cost of the network is not the amount of switches, but the amount of
lines, and I said there are log p, like lines of p connections. So I said that everything had, well, so there are p connections, right? So that's 1, 2, 3, 4, 5, 6.
It's
Yeah,
just
there are p
because in
connections.
the dynamic network they talk about switches, and in the static one they talk about lines.
Yeah.
In a way.
So my thing was correct, but it might not be the cost they ask for. I think this would be a toss-up if I would actually get this point. But yeah, for the other one, it's just straight up true. There's a 40 hypercube. I had that from the slides. So 40 hypercube, n log n over 2. Yeah, where here again just any hypercube, I think, right? Because it's the cost is O of n, and no, this is a mesh. This is not a this is not a hypercube, because this is more than just things linked together. No, yeah, it's just a hypercube. A 40 hypercube is an example of this, so that would still be true. For the 24 processors, genuinely no idea. I believe that this is correct. It makes sense.
Yeah, that makes sense because it's like it's 1 over f plus 1 minus f divided by the process, which is what you did here.
Yeah. So yeah, the only kind of reach that I see here is the fact that I wrote t parallel as t serial over the amount of cores, but like, yeah, there's no other way to express this entire thing in such a way that the t serial stripes out. So fuck it.
Oh, in the book, it does it the same. Like it expresses the fraction always as from the t serial the time.
Okay, nice.
So this is.
Yeah, we wanted output dependency. We thought this was output dependency because if you parallelize this, multiple things can override B, and that's an issue. Yeah, let's have a look at the slides over OpenMP versus MPI. I believe there was something on that in the slides.
Are you sure it was lecture 2 for seeing what is overriding or not?
No.
Yeah, it's lecture.
I think it was number 2 though. I'll
That's
check.
in my lecture 2 note, so.
Lecture 2. Scroll here.
There.
So output dependency, overwrite the same output variable. So that's what we did here. We overwrote B, which is an output variable. And while it's not directly used as an output, it is used directly again. So it is a variable that gets overwritten by two different things, which you wouldn't have sequentially. What are the differences between OpenMP, shared memory devices, and this is distributed memory devices. Its own memory space, yeah. Yeah, so we said shared memory and non-shared memory, which is not the exact perfect term. It's distributed memory.
It's exactly what it's on the slides.
Okay, lovely. Part takes up, yeah, so, like, this is just logic, right? Which part should you automate? The part that takes up most time. That's what you should try to automate first. And if you can't, you go to the next part. Or automate parallelize. Yeah, so this 8 was a pure guess, and I still have no idea if the answer is correct. Okay, it was the same approach to parallelize Jacobi for the Gauss-Streidel. Actually, no, I know this. And the reason I know this is if I go to the exam with answers, the yada yada. So we cannot simply partition the 2D grid and assign subgrids to each processor as we can for the Jacobi iteration.
Oh, yeah.
So we cannot use the same thing to parallelize Jacobi and Gauss-Streidel. Diameter and bisection bandwidth, got that from the slide, so that has to be correct. So log n and n over 2. Actually, I think wouldn't the exact number be log n and log n, or o n and o n over 2? I don't think so. I think these are actually exact numbers. Never mind. It isn't even log.
It's a lecture 3.
Oh no, it's not logs. It's just yeah, nice. Right, so that's correct. Communication time is startup time plus communication throughput times message length. Yeah. I don't know, man. This is just true. Don't know what to tell you, G. Does it say somewhere here?
I think it says it in the MPI one. I have a feeling, because I know that we have to do that in the MPI exercises.
Mm-hmm. Probably didn't save that, to be honest. So I'd have to look at the slides for section 5. So that is... So there is no lecture 5 because there's lecture 4, but there's 4.25.
Yeah.
Concepts. Yada yada yada.
Anything else? I feel like in quiz 3 they talk a little bit about it in one of the answers.
Mm-hmm, that's true. I do feel like they say something about it, yeah, in here.
They talk about it with alpha and beta, kind of that kind of formula.
Yeah. No, not here. I'll have a look at the previous exam answers.
And quiz 3, I think that's in there as well.
Oh yeah, we can have a look at quiz 3, sure. Like the answers are like, of course,
Yeah.
I believe. Answers to quiz 3, content quiz 3. Well, sure. This is such a fucking messy thing, honestly.
Yeah. I actually had sent him an email to ask if he could upload quiz 1 and 2 as well, because I couldn't find them before.
Lab session, lectures.
Now that he gave the
It
answers
isn't even in
as
there,
well?
is it? Quiz
Should be.
3.
Yeah.
No, this is just... Oh, the answers is in the assignment. fucking.
Believed it's some, or maybe I'm
No, not
wrong.
here.
It was somewhere though. Maybe it's in the.
No, I don't think it is.
Maybe it was the answers of the exam or something.
I think it's in the answer of the exam, because that's how I knew the previous one. I hate how fucking some lessons just don't give us the answers. Like, come on, bro. The fuck do you think we use this for? To learn. Yeah, so it's A plus MB, where B is the transmission speed, A is setup time. Yeah, this is exactly what I had.
And it's the message length, yeah.
And M is message length. Okay, lovely. Data parallelism versus task parallelism. Data parallelism we know from the previous answer, and task parallelism. Task parallelism for parallelization. Distributing tasks across different processors in contrast to data parallelization, which involves running the same task on different components of data. Yeah, okay, yeah, like that's... Yeah, so task parallelism, running many different tasks on the same time on the same data. That's what I wrote down. Yeah. Done on data where every thread gets its own task to perform on the D data. Yeah, that's one-to-one. Fuck you, got it. This one, yeah. Yeah, again, no way to know.
Although, Guy, you ran it, right, the code?
Yeah, you found a better way?
Yeah, the one code that I wrote there, if you go in the chat, with the reduction A, it works. It worked for me. For many rounds, it was even good answers.
Yeah, so could that be because your initial choice of variables is not optimal? Like it's all 0, 2, 2, 2?
Could be.
I would say try it with
when I
1, 2,
tried
3,
only
4,
with
5,
private,
6, 7, 8, 9, 10, 11, 12, 13, 14,
Yeah,
15, 16, 17, 18, 19, 20.
if I try only with private eye without the reduction, then I get the error.
Yeah.
If I do with 4 threads,
reduction
but with
plus-
reduction
plus A. So the reduction plus A. So the reduction plus A, the only reason that is working is because the initial value is 0. If the initial value wasn't 0, then
for A.
Yeah.
But before I tried with another different. But let me try again.
because reduction, I believe, combines all of them and combines them into one array from the 5 arrays that you have by counting them together. So you will have solved this in a different way. So yeah, you solve it in a different way than us. So we do this here where we move D up 1.
Yeah.
Um,
It didn't work.
yeah, so we solve
Not
it
that
by
I
moving A up 1.
Change.
Um,
Mm-hmm.
And yeah, you solve it by just adding them together, but that's not, that doesn't really work because of the...
Yeah, it didn't work.
Yeah. So yeah, we solved that here by moving this up one so that we're talking about the same thing, and that reliance is gone. And yeah, and then the other thing we solved was that D used to be like edited and then rewritten to, but the changes would always be ahead of what we were doing. So in a normal loop, that wouldn't matter. But here we just copy D, and because we copy D, we can just change E, or we can change D however we want, and we still have the old version of D in E. So yeah, we can just change it. So yeah, I'm about 75% sure this works.
I think this is good. I think this actually probably we've done too much here, because I feel with all the answers, it's just like, oh, just make a temporary array, copy it to that. He's not doing the whole thing. You have to write it out in code.
Probably the worst case scenario.
I think they literally asked us for the code. Like,
really, did they? Okay.
Yeah, so they said,
Oh, yeah?
give a possible solution such that the loop can be executed in parallel.
Yeah, exactly.
Okay, but in the other answers, it's always like, just copy it to a temporary thing or something.
Yeah, so we probably could have said, move the second iteration one forward, or move the indexes of the second iteration one forward, protected by a guard clause that says I not equal to an endless blue, and then compute the first one outside of the loop. This is less writing at that point, right?
No, true. It is nice and clear. I must say.
They can't misunderstand this. I mean, maybe they dot copy, but fucking it copies. Whoa, crazy. Call them this.
Yeah, and this one you also just said, sorry, I don't know exactly the line for C, so
Yeah.
I'm gonna feel super awkward writing code with my pen, but whatever.
Yeah. I really hope they're not gonna make me write code with pen. Honestly, fucking hate that shit. File sharing is when you the chunk of data that constantly gets updated so that you can't cache it, and you're waiting on the other ones. File sharing situations could occur when two applications running attempt to access the same information. Yeah, so file sharing, performance degrading pattern, coherent caches. Yeah, so when when you access data that isn't being altered, you can use the cache. But if it is being altered, the caching protocol must reload the whole cache block because you have to, because it's been altered, right? You don't have the most up-to-date version. So yeah, instead of being okay to use a cache, you have to go the long way around to get the memory. So that is what file sharing is, and we fix it here by putting it in a single variable called total and reducing it to a single variable at the end. Yeah, no idea. This just seems logical. I don't think I'm wrong here, but yeah, this was like almost the same as the previous one, and the previous one had this logic.
I agree. I think that we went through this, and
these two were just almost guessing. So these two were. This is 2017. These two were. Consider the difference. Yeah. What's the reason for applying? Yeah. So this one is 1-to-1 copies from the other one. For another one, can we still do it? We said no because that requires data from the next one, and we don't have that.
Yeah, which also we found in the other answer to the other question, right?
Well, sort of, not really. This was mostly a guess. This one was not from the other question.
Okay.
So the sixth one, so it is using Gaussian elimination. So that one, what Gaussian elimination does is, let's see. Oh, yeah, Gaussian elimination for tridiagonal systems.
And Gaussian
so this is recursive doubling, right?
But that's the next thing. Yeah, Gaussian elimination said that we can't do that. We can't parallelize that.
Yeah, so we can check that by going to parallel.
I can also look that up in the book. I've got it somewhere.
Yeah, I mean, I'm on the slides already at this point. 6, open, Gaussian elimination, sequential algorithm, LU, work distribution, LU, mapping into... At some point, it just becomes worth to not learn all this shit, because holy hell. This is like as much information as in the rest of the fucking... thing. Yeah, so this is a sequential process, which is because Gaussian elimination, what it does is it like takes everything below it and sets it to 0.
Yeah, the same way as in the other one in a way. it depends. Every step depends on each other.
Yeah. So.
It says also in the book, in this form, the Gaussian elimination or LU decomposition has to be computed sequentially and is not suitable for parallel implementation.
Yeah, so that one's correct. So there's only one number on the diagonal, only one calculation. We can't parallelize a single calculation. And iteration depends on past iterations, so we can't parallelize the laser. Zero speed up. And the idea of recursive doubling is you push the off diagonals further out by using the I minus 2t and I plus 2t equations to cancel each other out. Recursive doubling increases the computation cost and total amount of calculations done, but it also increases parallelizability. Because it's like you're pushing it out and out and out and out and out until you're completely done. And then you have a diagonal. And yeah, that's it.
We've done it also in 1.5 hours, which is good because we get 3 hours for it.
Yeah, but honestly, I don't know about you guys, but honestly,
What you're gonna do at that time? You can't look in the book.
Yeah.
So I mean, honestly, I not to go. Oh, I'm very fast, but I've never sat an exam out for the entire time, except for like maybe twice.
Well, I remember Guy usually is finished within an hour. Right, Guy?
Yeah. I don't stay. If I don't know, I don't know. If I know, I know.
Exactly.
I have other things to do.
So.
And nobody's giving me the answers in this school. So
and you guys didn't have like classical mechanics exams where you had like a 1 A4 page answer and one mistake at the end, and then you have to go through the entire thing again.
Oh no. So.
We're not like that. We've not had that.
One reason that we actually have. Oh, sorry, I'll talk through you. But one reason that like for computer science that like sometimes you take the whole time is because in computer science you get to do your own calculations, but you can also they give you tests to see if your answer is correct. So your answer is wrong, and then you can change your code until their tests pass, so your answer is correct. So like you'll just be like changing some shit up in the code and just running their tests to see if it works, and just changing some shit, running the code, changing some shit, running the code. So that's the only moment when I'm like when I spend too long there or that long there is when I'm like completely redoing or like rewriting my code every time to see if I can make it work. Right. Shall we soldier on to the last exam?
Yeah.
Good.
Lovely. Honestly, so far I've learned a fucking lot. This is like
Can
fucking
you
Really
send
nice.
the text of
And also where we have to do
Next.
more. It also shows you.
yeah. Let's just say.
to send the answers to me in
Oh
LaTeX?
yeah.
Like,
Sorry. I will. Back to your projects. Uncategorized parallel exam 2. Copy. New file. Answer. Probably shouldn't have called it answer1.txt because it's not really the answers, it's our answers, but whatever.
Close enough.
2.txt.
the answers.
Yeah, I've already named the first one, so I'll just fucking keep the same naming convention. It is in the general chat, so for the people that do not know, for the people watching the stream, in this general chat in the voice channel of the CSE server. If you don't have the invite, ask it to me. I'll send it to you. Right. Next exam.
Maybe you want to pause recording and start again. I don't know. Just have 3 files, one for each.
Yeah, not a bad idea. People who are watching along. First of all, good luck. It's like 1 day before the exam, Leo. Second of all, the next part will be in the description of this part.